Biologic drugs operate on precise geometric tolerances. An antibody's entire therapeutic function depends on its specific three-dimensional structure. If it fails to hold that structure and folds incorrectly, it ceases to be a treatment and becomes an immunogenic hazard. To manage these risks, the industry utilizes quality by design. This is a regulatory framework where developers treat thermal stability as a quantitative metric for developability. By mapping these precise limits during early manufacturing, researchers can fingerprint a drug candidate to ensure it remains functional from the factory to the patient. Differential Scanning Calorimetry, or DSC, is the primary tool for this fingerprinting. It measures absolute thermodynamic values by examining compounds in their native liquid state, requiring no exogenous tags or dyes that might interfere with the protein's natural behavior. DSC provides a direct reading of a molecule's resistance to thermal stress. This quantitative data ensures that every batch meets the strict biophysical standards required for regulatory approval and patient safety. The core mechanism of DSC is a thermal comparison. The instrument measures the exact difference in thermal power required to heat a sample cell and a reference cell at the exact same rate. Protein unfolding is inherently endothermic. As temperatures rise, the molecule must actively absorb energy to break the secondary non-covalent bonds holding its structure together. This animated graph plots that endothermic energy absorption against time and temperature. On the right, the clean, single-peak DSC curve tracks the exact heat flow required as the simulated protein structure on the left begins to unravel. The highest point of this curve is the melting temperature, or TM. This point represents a two-state system where exactly one half of the molecules have unfolded. Because the system is in equilibrium, the Gibbs free energy, delta G, is exactly 0. The total area beneath the curve calculates the enthalpy of unfolding, or delta H. Unfolding alters the molecule's interaction with the surrounding buffer. The vertical gap between the pre-melt baseline and the post-melt baseline reveals the change in heat capacity, or delta Cp. With direct measurements for melting temperature, enthalpy, and heat capacity, researchers can mathematically derive the exact Gibbs free energy for the molecule at any specified alternative temperature. While simple proteins produce a clean single peak, therapeutic monoclonal antibodies present a much denser structural puzzle. A complex IgG1 antibody is constructed of distinct primary domains, categorized here as CH2, Fab, and CH3. This line chart maps a multi-peak thermogram. Because the CH2, Fab, and CH3 domains unfold independently at varying temperatures, their individual heat signals overlap, appearing as structural shoulders on the main curve. To isolate the variables, engineers apply Voigt models, mathematically deconvoluting the overlapping signals into 3 distinct perfect bell curves, representing each specific domain. This mathematical separation reveals which specific structural domain will denature first, isolating the weakest thermal link within a complex therapeutic candidate. Calorimetry is subject to a severe biophysical trap. When a protein denatures, its interior hydrophobic regions are suddenly exposed to the surrounding aqueous buffer. To shield those hydrophobic regions from the water, adjacent protein molecules rapidly clump together in an uncontrolled reaction called aggregation. Aggregation is a massive exothermic event. It releases heat, which actively cancels out the endothermic absorption signal required to measure the protein's initial unfolding. Look at the graph on the left of this readout. Traditional coin sample cells trap molecules in tight proximity, allowing unchecked aggregation. The result is the sharp, jagged, downward exothermic drop seen at 90 degrees Celsius, rendering the thermodynamic profile unusable. Now compare that to the right-hand scan. Specialized hardware rescues the data, achieving a clean, stable post-transition baseline above 95 degrees Celsius. This success is achieved through the geometry of these twin-coiled metal capillary tubes. By forcing the sample through this narrow, elongated path, The hardware maximizes the spatial distance between individual protein molecules. Because aggregation requires protein-to-protein collisions to occur, this spatial separation mathematically delays the clumping kinetics. The instrument is able to finish capturing the endothermic unfolding event before the exothermic signal of aggregation can drown it out. Clinical testing requires analyzing these biotherapeutics in highly dilute physiological solutions, pushing the limits of sensor tolerance. Looking at this sealed internal chamber, a specialized pressurization system maintains a constant 6 atmospheres of pressure to prevent the aqueous buffer from boiling at high temperatures. Accurate readings depend on the copper-colored top plate thermoelectric device, which exerts tight temperature control with nanowatt sensitivity. This physical design uses a microscopic active cell volume of just 300 microliters, capable of generating a clear thermodynamic signal from as little as 2 micrograms of protein. Extracting high-resolution data from trace sample amounts ensures that scarce biologic candidates undergo complete thermal profiling early in the development pipeline. Identifying a stable molecule is only the first step. To reach the clinical shelf, that molecule must be formulated into an exact buffer matrix containing precisely balanced excipients and salts to prevent long-term degradation. Screening these formulations exposes the standard operational limit of traditional DSC. Testing one sample at a time and manually flushing the system between runs severely limits output. The mechanical limitation is solved by these intricate blue fluid channels, single-use, low-volume microfluidic flow cells. Integrating these microfluidic chips into a rapid screening DSC platform, researchers analyzed 24 distinct formulations simultaneously. This stacked line plot tracks the structural results. Processing the data in bulk exposes the vertical progression of the unfolding curves across dozens of staggered concentration increments. The inset scatter plot isolates the peak unfolding temperature against concentration, revealing complex, nonlinear stability behaviors obscured by single-run testing. Parallelizing the thermal analysis allows formulation teams to rapidly compare thermodynamic signatures, identifying the specific buffer environment that provides the highest relative stability for a drug product. Developing a biologic drug demands structural certainty. That requires calculating precise Gibbs free energy limits, mitigating the exothermic aggregation through capillary hardware, and parallelizing sample flow for mass screening. Managing this data volume requires the software dashboard shown here to automate curve fitting and execute batch processing with total consistency. Because calorimetry is the only method that directly determines the enthalpy associated with protein unfolding, it remains the definitive technique for characterizing higher-order structure. Subscribe to the channel to learn the mechanics behind the instruments driving modern biotechnology. Let us know in the comments if our next breakdown should cover the binding thermodynamics of isothermal titration calorimetry.